math, it's all about math, the wonderful world of math. Welcome to the wonderful world of math, trigonometry coming at you. We're going to do trig equations again, but this time we want to talk about unusual angles. What do I mean by that? Some trig equations we can solve basically by guessing, by having plugged stuff in to trig functions enough and knowing some likely outputs. So sine theta equals 1/2. We should be able to solve this by knowing which thetas make sine equal to 1/2. This is a common output, and the theta values that make this equation true are usual angles, for lack of a better phrase. By contrast, we have this angle. Sine theta equals 1/3. This angle theta is not a usual angle. It's not something we see a lot. This is an unusual angle. So we can solve this. And we can solve this. And there's important stuff to learn about this from this easier example. When we do the example on the left, we say sine is positive in two quadrants, right? In the first quadrant and in the second quadrant. And in this case, theta could be pi over 6, and in this case, theta could be 5 pi over 6, because that's the angle in the second quadrant whose reference angle is this one. Now, if I ask for solutions between 0 and 2 pi radians, that's it. But if I ask for solutions, period, if I ask for all solutions, you have to say pi over 6 plus anything coterminal to that. And you have to say 5 pi 6 plus anything coterminal to that. This, for any integer k, is the set of solutions, all the solutions. Some of the things we did here are going to be pretty familiar when we figure out how to do them for this equation. Now, this is really kind of a lot like the difference between the equation x squared equals 25 versus the equation x squared equals 26. We can solve this one basically by guessing. We know that 5 times 5 is going to be 25, or that negative 5 times negative 5 is 25. But in order to solve this equation, we need more tools. We need more help. We have this function, squared. And in order to get rid of that squared, we have to undo it. We have to do the inverse of squared. And the inverse of squared, for certain values of x, it's the inverse function, was the square root. The only answers to this equation, x squared equals 26, will be x squared equals square root of 26, or the opposite of the square root of 26. We needed a new function whose job was to answer this. And that's the same thing that we have here. So to answer sine of theta equals 1/3, we're going to use inverse trigonometric functions. And a lot like answering the equation sine theta equals 1/2, this is going to happen in two quadrants because this is a positive y value. There are going to be two quadrants where sine is positive. And to go from sine theta equals 1/3 to theta, this is what inverse trig functions were built for. You're going to take that positive y value and you're going to turn it into an x value between 0 and pi over 2, an x value in the first quadrant, our favorite first quadrant. But because inverse sine is a function, when you plug in 1/3 to this function, you can only get one output. You can only get this theta in the first quadrant. Now, this has an approximate value, and while you're doing this and getting used to it, it may be helpful to you to find those approximate values. I will want your answers like this, exact. Smiley face. Okay? So let's look at some of those approximate answers. In radians, using your calculator, you should be able to get this, 0.339837, approximately. And in degrees, it should look like this. Normally, I super want things in radians. I would prefer them to be exact, once again, smiley face. But while you're trying to figure out you're getting things in the right quadrants, it might be useful for you to put things in degrees where you have a better idea what the boundaries are for quadrants. You know that 90 degrees is the boundary between quadrant 1 and quadrant 2, and you know that this is definitely less than 90 degrees, right? So putting this in 2 degrees for now may help, but eventually we hope to not need that stuff and we can use radians directly. Okay, so tell me about this. It's not just going to be sine inverse of 1/3. We already know what that is. It only has one value. It's part of sine inverse being a function. Well, let's look back. When we had this, we had 2 quadrants, and we said that this angle was chosen because it was the angle in quadrant 2 that had this as the reference angle. That is what we want here too. We want an angle in quadrant 2 that has this as the reference angle. So I want you to look up what you know about reference angles and finding reference angles. Find the pictures that we used to come up with the equations that we used to find reference angles. Go back, look it up, pause this and go look, review. Okay, 3, 2, 1, we're back. Hopefully you found it. Hopefully you found that in the second quadrant we took an angle, theta prime, and we said that we were looking for an angle in the second quadrant with the same reference angle. What does reference angle mean? I hope you looked that up. If you didn't, now's your chance. 3, 2, 1, a reference angle is the positive, that means counterclockwise, acute angle between the terminal side of theta and the x-axis. So, in this case, this would be the reference angle. This angle is also theta prime. This one's just not in standard position. The angle in the second quadrant, with this as the reference angle, is the one that starts from the positive x-axis with vertex at the origin in standard position, right? That ends here. So this is our second solution. So we got all that out of the way. What's the important part about this picture? What can you tell me about this angle theta and its reference angle theta prime? Well, to get from here all the way and then here, you ended up going a full 180 degrees, pi radians. What that says is that an angle theta plus its reference angle, theta prime, adds up to pi radians. So that if you had theta and you wanted theta prime, you would solve this for theta prime. We find ourselves in the new situation of knowing the reference angle, this guy, and wanting the angle in the second quadrant, theta. So we subtract theta prime from both sides, and we will get pi minus theta prime. So if this is our reference angle, if this is our theta prime, then this is our second angle. And if you get numerical approximations of this, probably you'll get one in radians, but for the moment we're interested in the one in degrees. This is 160.53 approximately degrees. And you know that this is between 180 degrees and 90 degrees. This is definitely in the second quadrant. Knowing the degree measure of these approximations can help tell you whether you're in the right quadrant. You should also check that this plus this equals 180 degrees. It does. Great. So now if we want to take this one step further and say all solutions, not just the two solutions between 0 and 2 pi, or 0 and 2 on 360 degrees, we're just going to take the first one and we're going to say plus everything coterminal to it. And we're going to take the second one and we're going to say this angle and everything coterminal with it, where k is any integer. And these are all of the solutions to this equation. So let's try another example, a slightly different one. Here's one where we don't have sine alpha equals a number. We have to get it into that form. We have to isolate the trigonometric expression. So that means if we've got two terms, we want to have one term per side. We want to move this term to this side. We want to subtract 1 from both sides. So 4 times sine of alpha equals -1. And we don't want 4 sine alpha, we want sine alpha, so we got to get rid of this times 4. We do the opposite of times 4. The inverse, as you would say, of times 4. That's going to be divide both sides by 4. So you get sine of alpha equals negative 1/4. And now we're more or less in the same boat we were in a minute ago. We have sine of alpha equals a different than normal y value. But the question is still, which quadrants is this negative in? Sine is negative in quadrant 3 and quadrant 4. So we're looking for somebody in quadrant 3 and somebody in quadrant 4. We need to make sure what our reference angle is. So can we figure out the solution to this? Sort of. There's nothing else to do except to say the angle that makes this work is the angle whose sine is 1/4. Inverse sine of 1/4 is the only acute answer to this. So that is our reference angle. We need to find somebody in quadrant 3 and quadrant 4 with this reference angle. And last time we talked about how to do this for quadrant 2. Let's talk about how to do this for quadrant 3. So here we have a reference angle, theta prime. And now we're going to have somebody in the third quadrant, theta, right? And like last time, this is going to be about pi. You know that from here to here is pi. You also know that this, the way reference angles work, is the reference angle. So this is pi, and then this is the reference angle, and together pi and the reference angle theta prime make up theta. So pi plus theta prime equal theta. Now this has already got theta solved for, so if I want to know the solution in the third quadrant, I just take theta prime and add pi. And there we go. So how does this work in the fourth quadrant? In the fourth quadrant, we've got our angle, the reference angle, theta prime, and then in the fourth quadrant, we've got this, the mirror, this angle, also theta prime, but not in standard position. And then we have this guy, who is in standard position, whose reference angle is theta prime and is the angle in the fourth quadrant that we want to talk about. Now, the basis for comparing theta and theta prime is not pi this time. You should notice, however, that if I take this bit and I go theta prime more, I have suddenly made a full revolution, 360 degrees pi radians. So in the fourth quadrant, theta plus theta prime is equal to 2 pi. So if you know theta prime, this guy, and you want theta, you should solve this equation for theta. The angle in the fourth quadrant will say 2 pi minus sine inverse of 1/4. So now go ahead and find numerical approximations for each of these. Ready? 3, 2, 1, compare. We should have got roughly 194.48 degrees and 345.52 degrees. You'll know that this is between 180 and 270 degrees, third quadrant, and this is between 270 and 360 degrees, fourth quadrant. Marvelous! The last thing to do, since we asked for all solutions, is to say alpha plus sine inverse of 1/4 plus 2 pi k. Or alpha equals 2 pi minus sine inverse of 1/4 plus 2 pi k. Now can I simplify this in any way? Is there any way that I could, say, factor out a common factor between these two terms? And the answer is, you betcha. 1 pi, 2 pi k. They both have a common factor of pi. When you factor a pi out of this term, pi divided by pi, the only thing left is 1. When I factor a pi out of this term, there's still a 2 and a k left. So 2k plus 1 pi. And on this side, you get, factoring out a 2 pi this time, you can factor it a whole 2 pi out of the thing. 2 pi times 1 plus k minus sine inverse of 1/4. And this is for any integer k. One more thing I'd like to say about this before we do the next examples is that for this equation, we had that sine inverse of negative 1/4 is not a solution between 0 and 2 pi. Because of the output, the range of the inverse sine function, sine inverse of negative 1/4 is actually between negative pi halves and 0 in the fourth quadrant, but not between 0 and 2 pi, right? Go ahead and ask your calculator, what is arcsine of negative 1/4? It will tell you approximately negative 14.5 degrees. This is not between 0 and 360 degrees, so that's not one of the optimal first answers. If I ask you for 0 and 360 degrees, you won't get the answer right by picking arcsine of negative 1/4. And so instead on this problem we used the reference angle, sine inverse of positive 1/4, and used that to find angles in the third and fourth quadrants between 0 and 2 pi where we wanted them. Unlike in the previous problem, right? In this problem, sine inverse of 1/3 was positive, so sine inverse of 1/3 was between 0 and 360 degrees, or 0 and 2 pi radians. It was one of the solutions. If we take sine inverse of negative 1/4, it is not between 0 and 360 degrees. It is not between 0 and 2 pi radians. So we had to do this reference angle business. So we got a lot of stuff we talked about, mostly about reference angles. The range of inverse trig functions, also hugely important, kind of like every time you use them, right? So here's another equation. Find all solutions of 6 cosine omega equals 5. Like before, we're going to isolate the trig function. We're going to start by dividing both sides by the coefficient 6. Divide both sides by 6 and you get cosine of omega. Lowercase omega looks like an extra curly w. 5/6. Okay, great. So 5/6 is not a typical output. It is an unusual angle. That's why it's here. And the very first thing we're going to do is say cosine inverse of 5/6. What is this? Can you get an approximate value? Is it between 0 and 360 degrees? What quadrant is it in? Using the inverse cosine function, we should get approximately 33.56 degrees, or 0.585686 approximately radians. What quadrant is this in? It's easier to tell with degrees, right? That's the whole reason I've introduced degrees for the first time in ages. So if we're going to have two solutions, one of them is going to be in quadrant 1 where cosine is positive, and the other one is going to be in quadrant 4. There we go. So we're looking for an angle in quadrant 1 that has this as the reference angle. Hey, look at this is in the first quadrant. So one of the answers is omega equals cosine inverse of 5/6. Marvelous. And the other one in the fourth quadrant. How did we do that fourth quadrant stuff again? Why don't you look it up and come back? 3, 2, 1. Are you ready? Let's jam. 2 pi. Omega and omega prime, the reference angle, have to add up to 2 pi. So omega plus omega prime equals 2 pi means 2 pi minus omega prime is the angle in the fourth quadrant. In this case, the reference angle was cosine inverse of 5/6. So these are the two angles, and for all solutions, we simply say this and everything coterminal to it. So that means saying plus 2 pi k. And we do the same on the other side. And then we can simplify this a little bit if we want. And this is going to be our solutions. There we go. Find all solutions to 5 cosine of beta plus 6 equals 3. Start by isolating the trig expression. This has two steps. 3 minus 6 is negative 3. Divide both sides by 5. Cosine of beta equals negative 3/5. So the first thing we might be interested in, you might think, is that cosine inverse of negative 3/5? And the answer is sort of. At least this is going to be between 0 and 2 pi. I'm going to tell you that, much like our second sine example, this will be easier if we turn this into a reference angle first. Ask yourself, possibly with a calculator, what is cosine inverse of negative 3/5? You should find out that cosine inverse of negative 3/5 is approximately 127 degrees. Now, where is cosine negative? It's in two quadrants. The second quadrant, where this is, and the third quadrant. Ask yourself if it's easier to take this angle and turn it into this angle, or to take this angle and turn it into these two angles. I'm going to tell you that it's probably this one. And so what I'm going to do is I'm going to use the reference angle first to find these two angles. Although honestly, we've kind of already found one of them. Cosine of the reference angle, beta prime, will be positive 3/5. Why? Well, remember what reference angle means. It's positive and acute, which means that if you put it in standard position, it's in the first quadrant, where cosine is, understandably, positive. Great. So now what? Now we use inverse functions, and we say that beta prime is the inverse cosine of 3/5, and we turn this into angles in the quadrants where cosine is negative, quadrants 2 and 3. So how does this work? In quadrant 2, we take the reference angle and we flip it over to the second quadrant, where this, the positive acute angle between the terminal side and the x-axis, is also beta prime, just not in standard position. So that beta and beta prime add up to pi. Or, solving for beta, the angle in the second quadrant that we want, this is going to be pi minus beta prime. In this case, the reference angle was cosine inverse of 3/5, so pi minus cosine inverse of 3/5 is our angle in the second quadrant. In the third quadrant, what are we going to do? Well, here's beta prime. Here is the angle in the third quadrant with the reference angle. See, x-axis, terminal side, positive and acute. This is beta prime, but not in standard position. And you'll notice that this angle and this angle have a very special difference. That is, to get from here to here, not from here to the terminal side of beta, but from here to here. You should notice that it is 180 degrees, a straight line, pi radians. You may also recall that we described this slightly differently last time. Last time we said that to go from here to here was pi radians, and that to go from here to here was beta prime. But that to do it in one journey was beta. Hopefully you'll notice that if I add beta prime to both sides, these two are equivalent. Okay, so that's cool. This one, of course, gives us the equation that we want, where beta is already on one side by itself. What was beta prime? If you recall, it was this. So these are our two solutions between 0 and 2 pi. And again, I recommend that you check both of these with numerical approximations in degrees, because it's easier for us to check that. We know the boundaries better in degrees. So let's go ahead and check those and make sure. 3, 2, 1. And these are our approximate values. Notice that this is in the third quadrant and this is the second. Cool. So to go from here to all solutions, two solutions between 0 and pi radians, or 0 and 360 degrees, we just have to say plus 2 pi k. And of course, like before, we can collect like terms, factor out those pi's, and simplify it like this. So there's two sines and two cosines. See if you can try these. We don't have time to do the whole thing together, but I can write the answers and you can check your work. Mostly I want to know, do you understand the reference angles well enough to do this? Because if not, you should probably try to contact me. If so, you can use the sign examples and check it out. Try these. Try these at home. Okay, 3, 2, 1. Here's the answers for you to check your work. I hope you tried this at home. Tangent inverse of 6 plus 2 pi k, or in the third quadrant, where tangent is also positive, tangent inverse of 6 plus pi plus 2 pi k. Now notice that, or recall if you like, the period of tangent is different. I don't actually need to say tangent inverse of 6 plus everything coterminal to it. The period of tangent is pi. I could avoid having to write both of these things simply by remembering that tangent repeats itself after 1 pi, which is exactly where the third quadrant is, pi units later. So that takes care of those guys. And then we just say for all integers k. Same thing over here. Here, tangent is negative in the second and the fourth quadrants. But those are also pi units apart, it turns out. When you look at the reference angle, here and here, same reference angle, pi units apart. So we can get this instead. Notice though that pi and pi, you can factor out that pi, and we get this. And I challenge you to see if there is a better way to write this. There is. See if you can find it. And that's all we have time for today. Our constellation of the day is Boötes, the herdsman, and this has been a Badger Bear production of The Wonderful World of Math.